So in this class, we will discuss another problem on moment of inertia. Question is, find the moment of inertia of the section, so that is the shaded region, about the axis AB. So axis AB is defined here. So dimensions are given in millimeters. So this section consists of a triangle, a semicircle and a circle. So radius of circle is 20 mm, radius of semicircle is 40 mm. Height of triangle becomes 80 mm and width of the base of the triangle is 40 plus 40, 80 mm. So this total will be 80 mm. Now here he has asked the moment of inertia about the base AB. Since it is similar to the last problem which I have explained in the earlier lecture, so here we need not find the centroid of the composite section here. We have not asked the moment of inertia about the centroidal axis. Suppose we ask, then how to do that I will explain later in the same video. So here let us write down the expression for the moment of inertia of this triangle, semicircle and circle about the axis AB itself. So I write here IAB. IAB is the moment of inertia of the section about axis AB. About axis AB. So here this is given by IAB of the triangle portion plus IAB of semicircle portion, of course with respect to same axis AB, minus IAB of circle portion, because circle is a cutout portion here, it is a hole, therefore its a moment of inertia as well as the area becomes negative here. So we can use directly the standard formula which is available, which we have below. For example, for the triangle, so it is like this, triangle is like this. This axis AB becomes the base of the triangle. So this is 80 mm and this is also 80 mm. Now you know the formula in case of a triangle. You know the formula that moment of inertia of a triangle about its base is given by BH by 12. Directly you can use this formula. So AB becomes the base here. And that itself is the axis which is given axis here in the problem. So 80 into 80 cubed by 12. So this is the value of IAB for the triangle. So if you simplify this, you will get 80 into 80 cubed divided by 12. 3413. 3413 333. 0.33. So this is the value in millimeter power 4. So for the triangle, this is moment of inertia value. Next I will take a semicircle. If you observe the diagram, if you add the area of triangle and semicircle, and then if you deduct the area of the circle, you are going to get this composite area, that is shaded area. So 1 is triangle, 2 is semicircle, 3 is circle. So area A1 plus area A2 minus area A3 gives the area A. So here also this AB is nothing but the diameter axis. So this AB is the diameter axis here. Now the radius, you know, he has given the radius as 40 mm. So in this case what happens? The moment of inertia of the semicircle about the diameter axis AB, you know the formula, it is pi d power 4 by 128. For a circle it is pi d power 4 by 64. For semicircle it is half of that. So you can use pi into, since the radius is 40, diameter becomes 80. In terms of diameter I can write whole to the power 4 divided by 128. So if you simplify this value, so 80 power 4 into pi divided by 128. So this comes out to be 1005 309. 1005 309 0.65 millimeter power 4. So this is the moment of inertia of the semicircular portion about the diagonal axis. Now I will take the circle. So for the circle, what happens? The center of the circle lies on this AB axis. You can see the diagonal. That means AB is the diagonal axis here. In this case, the radius is given as 20 mm. So for the circle IAB, here the central axis as well as the diagonal axis is remains same. So you can take the formula pi over 4 by 64 for the circle. So d is 2r, 2 times radius, that is it becomes once again 40. So pi into 40 to the power 4 divided by 64. So this is the value of IAB for the circle. So if you simplify that, so what you will get is 40 to the power 4 into pi divided by 64. So it comes out to be 125663. 125663.71 millimeter power 4. This is for the moment of inertia of the circle about the diagonal axis here. Now you can see here that all the three values we have written with respect to the axis AB only. So axis AB for the triangle it is a base. For the semicircle it is the diameter axis. For the circle it is diagonal axis. So we have used the standard formula. So all these three are the standard formula. So therefore you can directly write the values, and after getting all these you substitute here. For the triangle the value is 333.33. Then plus for the semicircle 1005.309.65. Then for the circle it is negative because area is a cutout portion. Area is negative, moment of inertia is also negative. 125663.71. So these are the values. Now you have to simplify this to get the moment of inertia of the shaded region about the axis AB. Now let us simplify this. 3413.33 plus 1005.309.65 minus 125663.71. So the value is 979.27. So millimeter power 4. So this is the value of the moment of inertia of the shaded region about the axis AB. So please observe that in this problem I have not located the centroid because he has not asked the moment of inertia about the centroidal axis. He has given some other axis AB. So if you know the standard formula to find the moment of inertia of the simple figures, whatever here is this triangle, semicircle and circle. So about the axis which is given, then you can directly use those formula, just add or subtract whatever values are there, so to get the moment of inertia of the composite section. In the same problem, if he continues to ask also obtain the moment of inertia of the shaded region about its horizontal centroidal axis. Horizontal centroidal axis means it will be something like this. So you can see here the diagram is like this. This is the diagram. So this is the AB axis. So in this circular portion is cut here. So the shaded region is this. So this is what he has given. Suppose if he asks in this problem IGX also. IGX means it is the moment of inertia of the shaded region about its centroidal axis. So you have to locate the centroid first. So if you locate the centroid, it may come somewhere here, G. So you know how to locate the centroid. So you take the axis of reference, find out the centroid, locate the centroid, and this distance whatever you get between axis AB and this GX axis. So this GX axis is the centroidal axis. You note down the distance, and area is nothing but your total area A1 plus A2 minus A3, where A1 is the area of this triangle portion, A2 is the area of the semicircular portion, A3 is the area of the circular portion which is negative. So therefore A you can get. So once you get A and YC, YC is the distance of the centroid from the AB axis. Please note that. Then you can use parallel axis theorem to find IGX. Here is a reverse process, of course. So according to parallel axis theorem, IAB is equal to IGX plus A into YC square. So here you know these things. IAB you know, you have already calculated. A you know, YC square you know. Find out the value of IGX. So this is how we have to do. If they ask for the same problem, if they ask the moment of inertia about the horizontal centroidal axis, then you need to get the value of YC by locating the centroid.